So today's deliberation will be on introduction to finite element analysis, popularly known as finite element method. That is being presented by me, as it is one can see here in this slide. So this is a particularly numerical method and the most, so far, the most appropriate method. So before we start to know about finite element and its spread over various areas, we have to know that what does it mean. So in this case, as one can see, it's what is finite element method. It's as I have told just before a while that it's a numerical method, and basically and most frequently, rather to say most widely, it is applied to structural analysis. It's an approximate method, but doesn't mean that we can get the exact value. Exact value in the sense we can be very close to the exact value or to the exact solution, though it's an approximate method. So this method is implemented definitely in a computer, because whenever we have to use or we have to apply this to a very complicated structure or to a structure having various good number of nodes, degrees of freedoms, then there is no other option before us than to resort to this finite element method. The basic thing which it deals is converts the your governing differential equation of equilibrium in a member to simultaneous equations or matrices. So basically, it's a matrix method. We have to operate on matrices. As such, any kind of equation, if gets converted to matrices or simultaneous equations, then solution by a digital computer becomes easy. So before going into the details of finite element method, because in this lecture itself we can't go to the end of finite element method, it's just a vast sea or vast ocean, we can say. We have to just, my basic intention is to arouse a person in the Lawrence to take a deep sea of this vast knowledge. So here, we may say, first of all, I have taken the case of a beam. So here, as one can see, this is the shear force at the left end. This is the moment of, at the left end, which is clockwise in direction, and at the other end there is the incremental shear force with the original, that is F plus dF, and similarly M plus dm. dm indicates incremental bending moment or increase in bending moment, and this is a portion of the beam that's of length dx. The loading on the beam is of intensity q. It's a uniformly distributed load. With these forces and moments, the beam remains in equilibrium, as we have written it here, governing differential equation of equilibrium. So for that reason, what we have to see now here, that this force or shear force, as one may say, that's a differentiation of the bending moment. Then again, this if we go further differentiating this F, this will be the intensity of loading, as the intensity of loading has been marked here downwards. So this, it is negative of this Q. Q stands for intensity of loading. Then if we write the equation for bending moment, that is Jm, is EI d square W by dx square. This is an ordinary differential equation, and for that reason we are using the sign symbol D here. So E stands for Young's modulus, I stands for its moment of inertia, that's rather to say second moment of area. So EI in combination is called as the flexural rigidity of a beam, and this W is a deflection, downward deflection, and X, as we are seeing here, is the axis in the direction of length of the beam. Now again, the same thing has been differentiated here, and so d by dx of this differentiation of moment, as we are writing here, that means f is dm by dx. So df by dx will be definitely a differentiation of this entire thing, dm by dx. That will give us a fourth order equation, that is d fourth w by dx fourth, which will be equal to minus q. And this one becomes your governing differential equation. d fourth by dx fourth equal to minus q is the governing differential equation of equilibrium, because the beam portion has been kept, is under equilibrium, is in equilibrium under the action of forces and moments. Next we can come to a bar. So in the bar, let's see that we can here say that there is an axial force of intensity q. So if we take a small length of the bar, then that force acting in the direction of its axis will be equal to q dx. If this will be q dx, then as we know, area, this is the cross-sectional area of the bar, and here on this side, this is stress is sigma, axial stress of force here, and at the right end, there is an increment of d sigma to this axial stress. So in combination now, if we write the equation of equilibrium, that will be a dq acting towards the left, but if we take this to be acting to the right, then by just adding q into dx will be equal to 0 here. So in that case, d sigma, one can say that it is a product of Young's modulus of elasticity into increment in the axial strength d epsilon into plus q plus dx. That becomes 0. That's the next step here. Then we can again write for epsilon, that will become du by dx. Here u means the axial displacement, or the displacement along x direction, or along the axis of the bar. And here again, if the differentiation is, the bracket is open, this will become a d square u by dx square plus the intensity of loading, that becomes 0 to keep the thing in under equilibrium. The basic difference everyone must know before dealing with these equations, that a beam is a flexural member. Flexural means it has the ability to bend under loads, but a bar is an axial member, means it can carry a load along its axis only. It cannot take load transverse to its axis. So that's the basic difference between these two elements. Because in finite element method, we do use various elements. Here the example in this slide, there is a beam element, another is a bar element. Similarly, one can use frame element, shaft element, and there the degree of freedom will be different. Here in the case of this beam, we have 2 degrees of freedom per node, and here we have 1 degree of freedom. So these things will be discussed, because in the next lecture, here it is not possible to concentrate on within this time. Then why this FEM is actually needed? Basically for discrete structures, as we have seen previously, discrete means these things are discrete. Beam, bar, shaft, I may write here. So these are the discrete elements or discrete structures, means these can be dealt piecewise. But if we go to the next slide, it is written here, continua, means structures which are continuous in nature, means these properties like elasticity, mass, gets in that case is distributed all over the structure. So examples for this is plate, cell, etc. Plate means for for a common man you can say that this is something exactly like the slab of a building. Cell, some cylindrical cells may be found over industrial sites, and these things can be considered or can be modeled as two-dimensional or three-dimensional elements. Here the problem, why do you apply, as we have written in the heading, that why finite element method? This is because we can deal with things like this. Here, as it is written here, suppose there happens complicated boundary conditions, means different boundary conditions on different edges. Like here, suppose this is simply supported on this side of the plate, it is fixed. And next, we can see complicated loading. Now there is a axial loading here, and there is a patch loading here. In that case, the loading pattern becomes complicated. This is not as simple as the case of a beam, or that as the case of a point load. Then we can say complex geometry. If something like this, in example C here, this is a plate having a curved edge at the right end, and then there is a straight edge. There is a combination of straight and curved edge on this right side, having a hole at the somewhere within that plate. So this offers a complicated situation, and for this, writing a governing differential equation satisfying the boundary conditions as well as loading conditions will become quite difficult. So in that case, there is no other option than to adopt finite element method. Then comes complex material composition. Now you see this the simplest one is taken here. Suppose the plate consists of one portion as steel and the other portion there is aluminum. In that case, analyzing the thing becomes quite difficult. Suppose a plate having different layers in the thickness direction. So in that case, the layers having different amount of or different values of Young's modulus, Poisson's ratio, and mass density distribution, then these conventional methods will fail to solve the problem. Because writing the differential equation for this kind of complicated situation is quite a cumbersome one and almost a difficult one. Not difficult only, that's the most impossible one. Next we see that combination of different elements. Suppose in some structures, now there is suppose a slab is there, a steel rod or steel pipe of some significant thickness is now attached to a beam projecting out of the plate. Then in that case, there happens a combination of three kind of elements. One is plate, that's a continuum, that's a continuous thing. Then bar and beams are discrete things having different degrees of freedom at their nodes. In that case also, it will be very difficult to analyze this kind of structure by usual methods of differential equation of equilibrium. So these must have to be converted to some matrix kind of things, which is nothing but finite element method. Next we can go Then how does this method develop? How did it develop? That's a very important question here before us. In this case, we have to go back to year 1941, when Courant, in that year, introduced the use of triangular elements and interpolation and shape functions. So he was, while delivering a lecture in American Mathematical Society, that is AMS, as it is written here, he has given in his paper some introductory remarks and ideas about some kind of elements which were basically triangular. And in addition to these triangular elements, he has also suggested some functions which are interpolants, or we can say interpolation functions or shape functions. By this, actually, the basic, we can say, that's the core or the backbone of finite element method is interpolation functions. So then torsional rigidity of a shaft. Shaft is basically has to take the twisting or torsional loads. So that problem was being analyzed by Courant in his lecture. So in addition to this, that means simultaneous developments happen with his lecture in other fields, that is basically in aeronautics, about this finite element method. In that connection, we can say Turner, he belongs to Britain, Great Britain. He devised a three-noded triangular element. Then Teg also developed similar works and had also presented papers. Arteris applied principles of finite element method to matrix methods. Here something we should not get confused that what is finite element method and then what is matrix method. In matrix method, basically is applied to discrete structures like these bar, beam, shaft and frame elements. But finite element method is basically applied to continuous structures like plate and cell. But it is not, we cannot exclude finite element method from being applied to the area of discrete structures like bar, beam and shaft or frame elements. So in that case also we actually finite element method to be applied to basic discrete structures. We rather would have been written here. So in that case also there is a basic little bit of difference. As we shall proceed ahead, we can discuss these things. But for the time being and for the purpose of this lecture, we have to just confine ourselves to these introductory remarks. These two things are not no way different. Basically, both are applied to frequently different kind of structures, but there is a basic difference in the beginning only. Anyway, so Prof in that sequence, Prof in 1960 coined this word finite elements. Finite element means here a fixed number of elements, not infinite. So suppose we divide a structure, a plate, into 8 number of elements. So in that case, we say that this is a finite number of elements. So for that reason, the word was coined as finite element. Then Turner, Clough, Martin and Toff in 1956 produced a paper coining all these things. So next comes why it is so important and what are its spread, where it can be applied. In that case, we as initially we have mentioned, or even in the most significant part of the our lecture, we have mentioned that basically it is applied to structures, continuous as well as discrete structures. The other areas to which gradually this method spread is heat conduction. Means suppose one end of the plate is heated by some temperature, what will be or supplied with some amount of heat, then what would be the temperature at the other end or at some other point, having different sort of kind of material, different kind of fiber orientation or different kind of shape can be predicted by finite element method. Then comes seepage flow. That's a kind of this fluid mechanics type of thing. Here also this finite element method can be applied because when there happens some flow under the ground through soil of different strata, different permeability and different density, different kind of grain distribution, in that case also we can predict the amount of flow which will occur at, from one end to the other by finite element method. Then comes magnetic flux. It's similarly a kind of flow, electricity type of flow, means flux from one magnetic field has to flow through a material to other end. In that case also, that may consist of different electrical configurations. So prediction cannot be easy by any other method, and we have to resort to finite element method. Then comes microstructure study of in metallurgy. Here also, this suppose some metal is being mixed with some ceramic or some metal with another metal, then that was both of them are heated or in molten condition, these are mixed. Then what way the distribution will occur can also be predicted by finite element methods. Then can come chemical processes. In the chemical process, the amount of the amount of material input and the products, the rate of chemical reaction, the with the addition of amount some heat, some reagents, which are basically catalysts, can be predicted by finite element method. Then biofilm formation in some kind of biomaterials, a film forms, and the thickness of the film can well be predicted by taking inputs from the biomaterial by finite element method. Solidification problem, this is a kind of crystallography, all this belong to this metallurgy sector, in addition to this microstructure study. So all these complicated things are now being studied using finite element method. Then, what are the various forms of finite element method? As we have just seen that the finite element method usually has to resort to some kind of discretization, means it has to be discretized. Suppose we can say so here this plate element, this plate has been divided into 12 number of elements. In this 12 number of elements, we can see that the plate in the x direction, suppose we say this is the direction of x, this one is y, this is y. So in the x direction, it has been divided into 4 numbers, and in the y direction to 3, constituting 4 into 3 equal to 12 meshes or 12 elements. But in hierarchical finite element methods or meshless finite element method, there will be no mesh, only a single unit has to be analyzed. And here what happens? So this is basically the hierarchical method, and this one is a conventional finite element method. So or the usual finite element method. So here what happens? That happens a kind of polynomial degree or P refinement. This is called as P. The polynomial degree or order is refined for this kind of finite element method, but basically we do resort to this kind of finite element method where the discretization or the mesh refinement is done. This is a mesh refinement method. The purpose of these things are that suppose initially we take 2 into 2, two divisions along x and two divisions along y, means 4 elements, we may not get the exact result. But as we have written in the first slide, that with gradual refinement of the mesh, means if we increase the number of meshes or increase the number of divisions in the x and y direction, then gradually we can reach the exact solution or value of the exact solution. So in that case, either we can refine the mesh or increase the number of meshes, or we can increase the number of polynomial degree. That is called as P refinement. So these two basic things are basic things make a difference between these two types of finite element methods. Then comes partition of unit finite element method. So that's a different kind of finite element method, but cannot be built here. So next is what softwares are used in finite element method. There has been many softwares which are available, commercial softwares which are available in the market, like ANSYS, LS-DYNA, Abacus, Nastran. Perhaps ANSYS is the most widely used software. The languages which we can, with the help of which we can write a finite element code for some specific purpose are like this: Fortran, C, C++. Then MATLAB is not a language, MATLAB is an environment. We can write MATLAB. MATLAB is basically abbreviation of matrix laboratory. So in that, this is not a compiler like your C or Fortran. It doesn't have a compiler of its own. It borrows the things from C language. So what happens in MATLAB? There are most of the functions like inversion of some matrix, transpose of matrix, gets coded itself or are inbuilt in MATLAB itself. So just by giving some small kind of thing, suppose just for an example, we can say, suppose the matrix be A. So if someone just gives a dash like a thing here, then it makes it independent. So then there we can make easily the differentiation. D by dx can be done easily in MATLAB, or integration can also be made easily in MATLAB, but for which we have to write many lines if we use Fortran or C. That's a basic advantage which MATLAB possesses. Then what are the steps through which it works? So first of all, as we have discussed, discretization into number of elements. It is clearly shown in this figure here. So in this figure, as we are seeing, these circles represent nodes, and in this plate structure, the discretization is 2 into 2, 2 in x direction, 2 in y direction, and it consists of, each element consists of 8 number of nodes, as one can count, right? So that way, the discretization occurs here. Then next we go to form the element matrices. Element matrices are the stiffness matrix. If you are dealing with a vibration problem, then we have to write the mass matrix. And if you are dealing with buckling problem, then we have to write the geometric matrix. So these are the, we have to first form the element matrices, and then they have to be combined or assembled to global or structure matrices. Then the interpolation of displacement vector means, suppose for a plate, we say it will let it be having 5 degrees of freedom per node, and everything will be found in terms of the nodal displacements. But what will happen at any point within that element? For these reasons, this displacement, these interpoints are used. So the interpolation of this displacement vector has to be written, and then comes strain displacement matrix, that's popularly known as B matrix. This degree of freedom matrix can be written as D vector. This is not a matrix, this is a vector, means it has a single column. So then stress and constitutive relation, that is this is, we can write stress and constitutive or E matrix, right? Now conversion of load vector of any point into the element nodal load vector. Means we suppose the load is applied, let it be at this point, then it has to be converted to the nodal degrees, to the nodal load vectors by interpolation. There is a particular method called as consistent nodal loading, or even there is another method, that is lumped nodal loading. In lumped method, that's very simple. It just divides the entire load, total load, into the number of nodes happening in an element. But in consistent nodal loading, we use the equivalent work method. So these are the different things which have to be studied in detail. But the basic process is like this. So once this load vector is converted, then it has to be assembled like the matrix of stiffness and mass. Then assembly of the matrices, as we have writing here, global into global matrices. Then assembly of this global load vector. Then formation of global degree of freedom vector. So these things are basically very important, and that means this K here represent this one, global stiffness matrix, D global displacement degree of freedom vector, and R is global load vector. Now once we solve this thing, we get the values of D, means the degree of freedom values at each of these nodes of the structure are obtained. Once after obtaining D, we can process it to get the nodal stresses, means as we have to revert the process, means from degree of freedom method, we have to multiply this with B, this is strain displacement matrix, to get the strains. From strains, the constitutive matrix has to be multiplied to get the stresses. And then from this nodal stresses, we have to find the stress at any point within the element. So, but the basic difference is written here. This is for frame structure, means like or structures like beam, bar, shaft, and plane frames or frame elements. What do we do? That these steps in which have been marked by red things are not used. Means we need not have to utilize any interpolation function here. We need not have to utilize write the strain displacement matrix. We need not have to write the constitutive equation or conversion of load into element. No, up to this only. So here what happens? The things element matrices are formed by direct agreement. Means suppose the stiffness matrix. The stiffness matrix definition wise, the matrix for each element is written. Definition is simple here. Kij. Suppose, let me write for the stiffness matrix. So here what one can say, Kij means that the load applied in the load applied in the jth direction, right? When a unit displacement is occurring in the ith direction, to keep the structure under equilibrium while all other degrees of freedom are 0. So by this argument, one can frame or one can form the stiffness matrix for an element of the beam, bar, or let's say frame. Next comes yes. So basically, frame structures have been detailed here. Like suppose rigid frame may be there, flexible frame may be there. We generally tell this truss to be flexible frame. Then here it is as we have shown, this is a plain truss or 3D or space truss do belong to flexible frames, and to rigid frame we do write frame consists of columns and beams, which where the basic difference between these two things is that the angle between the members at a joint doesn't change in case of a rigid frame, and here the angle changes. Now, the thing like determinant truss or indeterminate truss is detailed here. So, in addition to all these things, the solution kind of it is written here that what we can solve, method of joint, method of sector, all these things are already known to the person studying the basics of engineering mechanics. But whatever has been studied in engineering mechanics like joint and section cannot solve a big problem. For a big problem, we have to apply matrix method or a form of this finite element method to get into the details or the forces in all the members. Now, before us, there are various types of elements. As we have told here, this can be this is the method by which we can write the stiffness matrix for a bar element. So next we can go to assembly of elements. How these things get assembled? Here, this is the global degree of freedom vector U1, U2, U3 for this one, because it's a bar member, means degree of freedom is along its axis only. So here is number first degree of freedom, then second, then third. So this is the degree of freedom. Direction is U. This is the. So here, first of all, suppose let's go to the member number 1 or member number A as it is written. So here, the first 1 and second degree of freedom corresponds to or coincides with the first and second degree of freedom of the entire structure. But for the second member, the first degree of freedom coincides with the second degree of freedom of the overall structure, and its second degree of freedom coincides with the third degree of freedom of the overall structure. So this way, writing these local and global nodes, we have to assemble it with correspondence to the proper degree of freedom, otherwise there will be error. So in this case, directly this will be 1 minus 1, as previously we can say here, one is AE by L, other is minus of AE by L. So one will be minus 1, the diagonal ones will be 1, and the off diagonals will be minus 1. And accordingly, we have to assemble this. Now here 1 minus 1, this is minus 1, this is 1. Again with this one, the thing corresponding to the second structure, means which is 1, has to be assembled here. So that will give plus 1. And for the other things, other node of this first second element, that will be minus 1. And here it will be off diagonal things will be minus 1, diagonal things will be 1. So this covers our assembly process. So with this, I think we have reached the end of this introductory session. So in future, we can present and we can discuss the things which will be which can go into the detail of these finite element methods or analysis.